Engineering from Assam Engineering College, Guwahati University, Assam, and holds a PG Diploma and Master of Technology from Department of Petroleum Technology, Dibrugarh University. She holds a PhD degree in the thesis entitled Flow Through Porous Media with special reference to enhanced oil recovery of Oil India Limited, Duliajan, from the Department of Petroleum Technology, Dibrugarh University. She was awarded the prestigious Indo-US 21st Century Knowledge Initiative Project by UGC in 2015 with the University of Louisiana at Lafayette, USA. The DST India-Tunisia project with SFEX University in 2017. UGC UKIERI Joint Research Programme project with the University of Edinburgh, UK in 2018, and DST-IC IMPEX Indo-Canadian project with the University of Ontario Institute of Technology in 2020. Her notable works were published in Springer, Elsevier, SPE, ACS, Taylor, and Francis, and many more. Dr. Borgohain Gogoi ma'am have to her credit 2 books. One is The Petroleum Technology, Enhanced Oil Recovery Techniques, published by Oxford and IBH, and the other one is Advances in Petroleum Technology, Enhanced Oil Recovery Techniques, published by Jenny Stanford Publishing, New York. May I now request Dr. Subrata Borgohain Gogoi ma'am to kindly take over the session. Thank you, and over to you, ma'am.
Thank you, Tanish, for you describing about me so nicely. Okay, I will be sharing my screen now. It's already shared. Okay, can you see my screen here?
Yes, ma'am. It is visible.
It is visible. Thank you, Dhruba. This is an AICT Training and Learning Academies program on faculty development. The theme of this program is Management of Hydrocarbon Exploration and Production Waste. So my topic of discussion today is management of hydrocarbon exploration and production through enhanced oil recovery. So going into this, I would like to first highlight the energy scenario of the world energy scenario during 2020. So this is in the left figure. We have seen that oil is 32.9%. The renewables which is coming up lately is 2.2%. Hydroelectricity is 6.7%. Nuclear energy 4.4%. Coal is 30.1%. And natural gas 23.7%. So this is the energy scenario as on 2020. But after simulation for 2035, the energy scenario for oil has gone down, that is 27.4. The renewables a little bit higher, that is 6.4. Biofuels 0.7. It came into entry, biofuels. Earlier it was not there. So hydroelectricity, there you can see that is 7.1. Slightly more. The nuclear energy 4.9. Coal has dropped down because of its emission, global warming effect, that is 27.1, and natural gas 26.4. So natural gas also has increased because of its less impact into the environment. So these are in million tons of oil equivalent, which is 41.868 gigajoules. So world's conventional energy, these figures are the latest figures of 2021. So non-recoverable oil, 4120 gigabarrels, So the recoverable oil is 3,000 gigabarrels, and of this recoverable oil, we have produced so far is 43%, and the rest 57% still unexplored. It needs to be produced. And for the unconventional oil, which is shale oil, shale gas, oil sand, CBM, all these are unconventional. So the recoverable is 2210 gigabarrels, and the remaining, the oil that is produced so far is 90 gigabarrels only, that is only 4%. And the remaining 96%, it is yet to be explored. So these are the whole oil in million barrels per day production. So you can see the natural gas, liquids, the non-conventional oil, crude oil, that is the additional crude oil. This is the portion which is in brown, additional by enhanced oil recovery, and the crude oil field yet to be found is this pink one. Crude oil field yet to be developed is this light blue one, and crude oil currently producing is this much. So it's slightly decreasing the production of crude oil. So it was highest in 2008-9, and slowly it is decreasing in a decreasing trend. So this is the global oil scenario. 40,000 oil and gas fields discovered onshore and offshore, and 94% of oil is from 1,500 fields only. So for the light oil, we categorize the oil in terms of API. So light oil, which is greater than 25 API, is 9.4 discovered in trillion barrels. Medium or heavy oil, 11 to 25, 1.5 trillion barrels are discovered. And extra heavy is less than 10 API gravity. It is 3 trillion barrels. API gravity is 141.5 divided by specific gravity minus 131.5. So higher the API gravity, lesser will be the specific gravity. We Indians are interested in the middle or the heavy oils because we are more interested in the kerosene and the diesel fraction. But the US and the Western countries, the rich countries, they're interested in the lighter distillates. They're more interested in motor spirit, which is otherwise the petrol fraction. So the produced oil is 10%, and undiscovered oil is 90%, and medium to heavy oil is 11 to 25% production, and extra heavy, that is the bitumen and the asphalts, is less than 11%. So in terms of location, we have current average world is 22 recovery factor, US 39, North Sea, UK, it is 46, and technical attainable is 70. So this is the latest global oil scenario as of 2021. So onshore and offshore oil production, relatively the much higher is the offshore production. But India, interestingly, we are also into onshore, but we are also doing onshore in the Assam basin, mainly in Assam, Upper Assam, we have all the fields onshore. We don't have offshore here. Offshore is located in Bombay High. So the production from Assam basin is 4 million metric tons per annum. And from Bombay High, it is nearly 26 million metric tons per annum. But the requirement in India is 240 million metric tons per annum. And this is being the rest, more than 80% is being brought from outside. So this is the latest scenario. And for recovery by enhanced oil recovery, for carbon dioxide miscible flood, The recovery is this much. This is the global scenario. We don't have carbon dioxide in India so far. Carbon dioxide enhanced recovery is not been implemented in India so far. The hydrocarbon miscible flood is this much. And more you can see the steam flood, which is also in India, in the Rajasthan area, where they have the heavy oil. And this is the chemical flood. Chemical flood we do have in Assam, Upper Assam Basin, but it's in 2 or 3 locations only. Then you have the combustion, which can be categorized as a secondary recovery process as well. Then onshore and offshore oil production 2021. For offshore, it is 28%, and for onshore is 72%. So oil recovery by enhanced oil recovery, you can see here for carbon dioxide is this much, the 11% for carbon dioxide immiscible. Carbon dioxide miscible is 11%. This is immiscible is very less, that is 1% only, and hydrocarbon miscible, this is 31%, chemical is 2%, and steam is 54%, and combustion is just 1%. This is the global scenario. So half of world's production, which comes from the 100 biggest fields, almost all of these are over than 25 years old. So they are old fields. So production from old fields is depleting. So we need to go for enhanced oil recovery. You can see here in the graph that the enhanced oil recovery is producing more of oil than that of the new recoveries. The new recovery is very less. So this is the latest world scenario. So you need to go for enhanced oil recovery instead of new recoveries, because in new recovery you need to drill a well, which is also very costly, economically not viable when the crude oil price is so low after the COVID situation. So this side is the oil viscosity, and this side is the in the y-axis is the reservoir depth. So in terms of oil viscosity and in terms of reservoir depth, we have categorized the floods, the enhanced oil recovery. So this is the screening criteria for enhanced oil recovery, or IOR. So this is you can see this blue one, which is the immiscible gas injection. The green one is a chemical enhanced oil recovery. The thermal enhanced oil recovery can have an oil viscosity of a wide range, and the depth is also very shallow. For in case of pattern flood or bottom water injection, the depth is quite large, but the viscosity is very less. And in case of miscible flood, you can see here the depth is quite more. You can use it for a longer depth, but the viscosity is very less. So this one is the capture mechanisms. Inside the reservoir, we have 2 capture mechanisms. One is the interception capture mechanism, and others is the staining capture mechanism. So this is the oil blob. So this, usually we call this not the droplets, we call it as blob. Blob means it's somewhat like oval shape. So it is not exactly a droplet-like. We normally call it a blob. So oil blob, when it gets stained in the throat, this is the throat area and this is the pore. This is the pore, this is the pore. So when it is being intercepted on the surface of of a grain, then it is the interception capture mechanism. The other capture mechanism is the straining capture mechanism in the throats. This is in the throats. So these stained blobs are very difficult to remove, but the intercepted blobs can be removed by the secondary recovery process like water flooding and steam injection. It can be removed, but these stained blobs cannot be removed easily. So it needs exotic fluid for its removal. So exotic fluids means it can be chemical, the microbial, heat, anything can be exotic fluids that is not actually present inside the reservoir. The conventional fluids are natural gas and water that is present inside the reservoir. So the cost of enhanced oil recovery. The highest cost you can see in terms of US dollars per barrel is for the surfactant flood. Carbon dioxide flood is also costly because the surface equipments required is very, the MOC and other surface equipments are costly. That's why it's costly. But here the surfactants are costly. So surfactant chemical floods are costly, and the thermal flood, you can see the thermal flood is slightly lesser cost. And compared to surfactant, polymers are cheaper. Normally we use the polysaccharides, the natural polymers, and the water flood is the cheapest. This is the water flood, and microbial is also cheaper. But this microbial is still in the development stage. In case of microbial, we get both the microscopic and the macroscopic efficiencies of the reservoir. In the polymer flood, we get the macroscopic sweep efficiency of the reservoir, and in the surfactant flood, we get the microscopic displacement efficiency of the reservoir. In carbon dioxide flood, we might get both because it depends whether it is immiscible or miscible. And similar is the case for thermal flood. For water flood, normally the dominating factor is the macroscopic sweep efficiency of the reservoir. So this is the primary recovery process, the natural flow and the artificial lift and stimulation. So this is the secondary recovery process. This whole area is the IOR. You can see this whole oval one is the IOR, but EOR is a subset of IOR. This is EOR, and we have for EOR primarily we have the chemical EOR. Then inside the chemical EOR we have the foam EOR, which is surfactant with carbon dioxide. Normally, that is how we make foam here in our lab. And then we have the nanofluids, the surfactants, alkali, and polymers. This falls under chemical EOR. And the ASP is the alkali surfactant polymer, and surfactant polymer, AP and AS. So here I have categorized the chemical floods. You can see the chemical floods, the foam and the nanofluids, and this you can take either two of them together, or you can take all three of them together. Okay. It depends upon the reservoir conditions also, the way you take the miscible floods. So this is the miscible gas injection. We have the alcohol slug injection here, and the LPG slug, and the thermal. And this is the enriched gas injection. Otherwise, it is a condensing gas drive, and high pressure natural gas injection, or the vaporizing gas drive. So these are the different miscible floods that we are applying here in Upper Assam Basin, not the LPG and the alcohol, but these two are in application here. And for the chemical flood, we mostly have the surfactant and the polymer. And for this, we normally have everything, artificial lifts and natural flow. Okay. Then enhanced recovery is actually the introduction of exotic fluid, as I have mentioned. And this one is the introduction of both the exotic and the conventional fluids. The removal of immobile fluid, mainly the removal of immobile fluid, is described under enhanced recovery. And this is removal of both the immobile and the mobile fluids. The intrinsic properties of the reservoir fluids are changed in case of enhanced recovery, which is the primary target. And this one is no change. And sometimes the intrinsic properties are also changed, because I have told you that enhanced soil recovery is a subset of IOR. So thermal flood, this thermal flood, the yellow one I'm describing here once again. This thermal flood is hot water injection and in situ injection. So hot water, normally we inject the heat from the surface. In situ injection is inside the reservoir, we put a heater or a furnace to heat the fuel. And this one is hot water. And normally hot water, when you inject from the surface, it turns to be cold water on the, not cold water, the normal ambient temperature water on the inside the reservoir, and hence it becomes a water flood again. The saturated steam, and of course it loses its temperature while it is flowing through the well bore, and then the cold water. And in situ, we have the forward combustion and the reverse combustion. In the forward combustion, we have the heater just placed below the injector well, but in the reverse combustion, we have the heater placed in the production well bottom. Okay, this on the forward combustion, we have the wet combustion and the dry combustion. So this is wet combustion also is categorized. That means water is also mixed with air. Here, dry is only air introduction. And so this is a combined thermal drive for wet combustion, and this is cow, which is a combination of forward combustion and water flooding. So this is a combined effect. So ultimately, this particular flood of thermal flooding is the best for recovery. So this is a technical screening criteria for chemical enhancer recovery. Normally the API gravity should be more than 20 and the viscosity in centipoise is greater than 35. The composition is light intermediate hydrocarbons are desirable for miscible and high acid number. So this is high acid number is mostly desirable for the alkali flood, because alkali needs to react with the acid in the reservoir, and it makes a surfactant. And ultimately, apart from alkali changing the wettability, it also changes the IFT of the reservoir fluids. That is, it decreases the IFT between the oil and water. So this is the oil saturation percent pore volume. So formation water salinity should be, the chloride should be less than 20,000, and this divalent should be less than 500. Divalent causing lots of problem in the chemical flood. It leads to absorption, it leads to corrosion of the formation damage as well. The type of formation is sandstone is preferred. Our reservoirs in Upper Assam Basin is sandstone. That's why we are targeting the chemical flood more than other floods. The API gravity in Middle Darcy is greater than 50, and the depth is, so Upper Assam Basin, the maximum depth is 5,600 meters. So here the depth is as expected. So this is mainly the Dipam reservoirs and the Peral reservoirs are going for this chemical flood, which is having a little bit shallow reservoirs compared to the Yosin, mainly the Lakadang area, which is much deeper than the Yosin. It's cannot go for chemical EOR. But presently we are being producing from the Yosin, particularly from the Lakadang area reservoirs. So we are although we have targeted the chemical floods for the barrels of Narcotia and the tip arms of Dick Boy, but we cannot sustain it more because we are dipping more, we are sucking from the bottom of the barrel at present. The reservoir temperature is quite normal here, like the reservoir temperature is below 100 in Upper Assam Basin. So selection criteria of chemical enhancer recovery. So type of reservoir, you should know the type of reservoir, the rock mineralogy, clay, of course, the clay type, the montmorillonite, morillonite, smectite, elite. All these are the clay types present here. And the kaolinite. If the clay type is montmorillonite, then it is dangerous because it is a swelling clay and it will obstruct the pores and the throats of the porous media. The reservoir heterogeneity. The reservoir heterogeneity in Upper Assam Basin is more than 80%. So all reservoirs except the various reservoirs of US is homogeneous reservoir. They say it is 30% homogeneous heterogeneity, but still they consider it as a homogeneous reservoir. But our reservoirs are very heterogeneous reservoirs. So this is the reservoir page on thickness, the absolute permeability and the porosity. The reservoir temperature, reservoir oil properties, and residual oil saturation, salinity of formation water, and presence of bivalent cations. As I mentioned, these are dangerous cations if it is present inside the reservoir. Then adsorption will be more, reservoir damage will be more. Okay, I've just brought this slide to show you. Actually, we are targeting, this is the gas cap. It is an anticlinal reservoir having a gas cap, and this is all here. So this is the block of sandstone, the conventional core. As you can tell, it's a macroscopic scale in the macroscopic scale. And in the microscopic scale, you can see the grains here, the brown one, and the darker shades one are the throats and the pores. It's the sandstone grains. So this is what we can picture the reservoir as. So chemical EOR, these are applied in tertiary mode to mobilize the oil in pores held by the capillary pressure forces. So to reduce the residual oil saturation. This can also be applied in the secondary mode in combination with other displacement processes such as water or gas. So we can apply in the secondary mode when we try to make smart waters. The primary target of making smart water is wettability change. You have to make it more towards the water wet. Interestingly, the reservoirs of Upper Assam Basin are all water wet reservoirs, except the Borhola reservoir belonging to ONGC, which is supposed to be all wet. So main mechanism is in surfactant assisted chemical EOR, the reduction of IFT between the fluids, that is the oil and the water, or the brine, you can say, where the chemicals are being injected inside the brine, and the chemicals we take is water soluble or brine soluble chemicals normally, the surfactant and the polymers. The wettability change is a very important criteria for chemical EOR, and this change is mainly done by the alkaline group of chemicals. And the solubilization, we need to make it a solution so that it becomes miscible. And improving the microscopic displacement efficiency of the reservoir, this is the main target for surfactant enhancer recovery. For the polymer-assisted chemical enhancer recovery, it is the mobility ratio. We need to play with the mobility. We need to play with the viscosity of the fluid. So normally we play here with the viscosity of the oil. We try to reduce the mobility ratio. Mobility ratio is the ratio of the viscosity of the displacing, or is the ratio of the mobility of the displacing fluid by the mobility of the displaced fluid. We now try to reduce the ratio to less than 1, but we are in the reservoir condition, we try to reduce it to less than 10. So improving the macroscopic sweep efficiency of the reservoir is the primary target for polymer flood. So this is a polymer flood. You can see this is the oil bank after water flood, oil bank after the water flood, the alkali surfactant slag. So this is the alkali surfactant slag. So this is alkali surfactant slag, which is being pushed by polymer. So this will enhance the microscopic displacement efficiency of the reservoir and this mobility ratio, and this will enhance the macroscopic sweep efficiency of the reservoir. This is a tempered polymer which will act as a pusher towards this. And this is the driving fluid, again the brine, and the remaining oil is the residual oil saturation after this. So you can see this is the surface facilities. So surface facilities, the injector fluid, the injector well, and this is the production well. And again, this is also injector well. This is, I'm showing one portion of a 5-spot pattern. So advances in the area of surfactant and polymers. High performance surfactant have been developed which tolerate salinity up to, you can see here, 1 lakh ppm and 2500 ppm bivalent ions. So as I mentioned, bivalents are dangerous. So you need to select the surfactant that is tolerant to the bivalent ions. The silicon surfactant shows very low absorption. So this is a new entrant in the field of enhanced oil recovery, the silicon surfactant. So this, if you can target it in the form of nanoparticle, is much better because it will improve the surface area. And then if it improves the surface area, the reduction in IFT will be better. The blends of surfactant, instead of using a single surfactant, we can also use blends of surfactants together. See which blend is, the IFT is the least, and the CMC value, also the CMC is attained as at a lower concentration. Surfactants are available which are thermally stable to 260 degrees centigrade. Our reservoirs, as I mentioned, as not so hot reservoirs, at the temperature is between 80 to, you can say, 95. So some reservoirs in Middle East are having temperatures more than 200 degrees centigrade. The recent R&D studies indicates that the sulfonated acrylamide copolymers can tolerate high bivalent cations and temperatures up to 120 degrees centigrade. So 120, we don't have reservoirs of that high temperature reservoirs. Of course, some fields of Uncle Ashore is having temperatures as high as 120 degrees centigrade. So this is the surfactant classification. We have in hydrophobe and a hydrophilic head. We have a hydrophilic head and a hydrophobic tail in a surfactant. Normally, we use the anionic type of surfactants because our reservoir minerals are also anionic. And if we use the cationic, which is a positive, which has a positive charge, if we use this, then there will be attraction. So anionic, the reservoir minerals are normally anionic in nature. Therefore, we use anionic so that absorption is lesser. We have also targeted the non-ionic. And the deuterium, of course, we did not target. We are using normally Napara Basin, the anionic and the non-anionic type of surfactant. Non-anionic type of surfactant are very efficient in the reduction of IFT. So types of surfactant used in enhanced oil recovery, types of surfactant so this is the types of surfactant used in anionic mixer. Normally, I have told you that anionic surfactants are used. Some blends are also being used here. So surfactant used for enhanced oil recovery. This is normally we use the petroleum sulfonate, which is cheap and easily available. It is a product of petroleum itself. It's a product of crude oil. But for reservoirs with temperatures low salinity and bivalent cations, this cannot be used, this petroleum sulfonate. Then we have to target the alpha olefin sulfonate, the internal olefin sulfonate, and EAS, that is alkyl aryl sulfonate, and the ethoxylated alcohols. So this is normally for the high temperature application, AAS. The thermal stability of the surfactants are as follows. AAS is highly thermally stable, followed by IOS, EOS, and PS and EA. So these are findings from the research works of our students in the lab. So limitations of enhanced recovery. So adsorption, as I have told you, adsorption onto the surface. We have to study the adsorption isomers, isotherms, and see whether it is chemically adsorbed or physically adsorbed. If it is physically adsorbed, then it is well and good. You can also remove it by applying some other chemicals. So adsorption is this one. So it has got a hydrophilic head and a lipophilic or the hydrophobic tail. So adsorption is a monomer of surfactant. It's a monolayer. You can see monolayer surfactant. It's a monomer surfactant. And this is the adsorbed polymer. So this is a polymer. So polymers also getting adsorbed onto the surface. This is polymer and monomer of surfactant. So surfactant will form micellar at the critical missile concentration. So this one you can see it is a conglomerate of polymer and surfactant together. So usually when it is of this form, it is not being adsorbed. So surfactant and polymer together is normally not adsorbed, but surfactant alone and polymer alone is getting adsorbed onto the rock surfaces of the reservoir. This has been studied in the lab itself, and this was found that the adsorption decreases when you use a slug of surfactant and polymer. So this is the monomer. This one is monolayer, and this is where this is you can see it is a multi-layer. It's a multi-layer adsorption. So highest temperature and high salinity limits the application of chemical enhanced soil recovery. Reaction of alkali with the clays. Alkali will react with the clays, and swelling causes permeability reduction. So if there is swelling, mainly if there is monomorillonite clay, there is swelling and it reduces. If there is smectite sometimes get transformed to monomorillonite, then also it is dangerous. So this is a surfactant having a hydrophilic head and a lipophilic tail. This is oil loving and this is water loving. So this is a monomer in surfactant. You can see this is the water loving. So water, so all the heads are coming towards water. And this is a formation of aggregates. Micelles is trying to develop the micelles, and this is the micelles. After it has attained a critical missile concentration, this is the micelle. And micellar formation in water in oil. This is the micellar formation in water in oil emulsions. So this is a change in wettability. This is water wet, and it is a mixed wet. You can see this oil is in the center. It's water is attached to the rock, and here it is a mixed wet, and this is oil wet. Oil is attached to the rock surface. So effects of interfacial tension during alkali surfactant flooding. So water injection is there. So these are the oil blobs here. Oil blobs kept by pore throat restrictions. This is a throat area. Oil blobs are there attached. So yeah, this is a staining capture mechanism. So already the intercepted captured blobs are being removed by the secondary recovery process. The staining capture, you have to inject it, trying to inject water, but it's not being removed. So you have to inject a slug of alkali and surfactant. Then this one will get removed. These oil blobs will become mobilized because the IFT reduction will be there and it will get mobilized and pass through it. Oil blobs passes through the pore throat restrictions, low IFT. So performance of ASP flood. So this is the oil rate till February 20th. This is simulation result, or this is oil rate, oil production, and this is the water production, and this is a base oil rate. So you can see the production of oil declining with this water cut increasing for ASP flood till this is simulation up to February 22. So this is SDS, the sodium dodecyl sulfate. So the production performance of sodium dodecyl sulfate. So it has been, the flood was done initially by water. You can see different percentage of SDS. These are the lab results of the students that I am presenting, already published works of the students. So this is the percentage oil recovery. You can see here the percentage and 0.3, and this is the highest when the percentage water cut 0.3 as the 0.3 percentage as the solution. So it depends on the what type of or how much of SDS you're putting, and accordingly consider oil and water cut here. So after injecting SDS, you see there is a shoot in the water cut here, the rise in the water cut, and similarly there is the rise in the oil recovery as well after injection of SDS, and followed by chase water. Chase water is there because to improve the macroscopic sieve efficiency of the reservoir, and this will improve the microscopic displacement efficiency of the reservoir. So performance of polymer flood. So this is a polymer flood performance. It's a simulation results of the experimental results that is obtained in the lab. And then, so this is commercialization. And then you can see the oil production. This pink one is the oil production. And this one is the water cut, the increase in water cut here. Slowly the increase out, but it is controlled increase in water cut. So we are producing from Upper Assam Basin, we are producing with a water cut of 98% also. Moran oil field is producing only 2% oil and 98% water. So this, because our fields are very old and we are still producing in the secondary recovery process in case of Moran. But Naharkotia has used polymer and the alkaline and the surfactant flood. They have been producing by the enhanced oil recovery process. So this is a portion of the 5-spot pattern. So this is the injector well, and you can see how it is the mobility effect. Slowly, these are the fingers coming up. So with different mobility ratio 0.2 or 0.15, the flood is quite stable. For one, it has penetrated, breakthrough has taken place, but the coverage here, breakthrough it's uniform. And this one for mobility ratio 2.6, there are fingers coming up. And breakthrough has taken earlier in the life of the reservoir. And this 6.7 mobility ratio, the breakthrough has taken quite earlier. the recovery rate is poor here, and you can see 18.3 and 84.5, there is the least recovery. There is no sweep. Much of the empty spaces in the reservoir is seen here. The sweep is not proper here. So this is a poor volume injected, the cumulative oil recovery. So this is Gentham gum, and this triangular ones is the 1500 ppm Gentham gum, 3% water cut, and this one is 1500 ppm Gentham gum, 10% water cut, and this one is 1500 ppm Gentham gum, and this is oil production. This one is the rectangular ones is the oil production, and this is the circular one is the oil production. There is a slow rise in oil production, and with a decrease in water production, and finally water production again increases. Here, some amount of, for this one, after shooting up of the poor volume injected, poor volume, after one, there is a craft rise in water cut. So this is the PMES. This is a new entrant in the field of chemical, that is a polymeric methyl ester sulfonate. So this also is being used in the reservoirs. We are trying to use this. We have given this to our US partner university, most probably because in India they are not giving us a candidate reservoir, so we cannot estimate the performance of this type of floods. So let's see if it is applicable, because in US every university has got a candidate reservoir and they can do the experiments there in the field. But in India, what's happening, we are only doing the lab work, and candidate reservoirs are not given to us but exploration companies. So this is this is a hydrolyzed polyacrylamide. So this is 4 arms. It has got 4 arms. It has got 8 arms and 13 arms. And if you increase the number of arms, better will be the recovery, better will be the sweep efficiency of the reservoir. So you are this branch, right? So you can see these arms are increased. You need to increase the arms, and you need to see under the microscope how is the arms increasing in the polymer. So this is a water plot, and this is a polymer anode. As the arms increases, the hyperbranch, when it is hyperbranch, the recovery is better compared to the single branch or 4 arms or 8 arms. When it is it has got more arms, the recovery is much better. So these 2 slides are, that is why I've shown these 2 slides to you. So similar is the case here for SDS. So this is for SDS. This one is, you can compare. So all recovery comparison between SDS and SDS PA. So this one is the comparison of oil recovery. So this one you can see for SDS what is, so when you are, this one has this violet one, this is a combination of SDS PHPA, has the highest oil recovery. So when you take a combine of surfactant polymer, then the recovery is much better. So this is a polymer molecule. This is a polymer molecule. You add surfactant to it. This one you can see a head and a tail, that is a surfactant, symbolizing a surfactant having a hydrophilic head and a lipophilic tail. And then you add more surfactant to it, you get a micellar-like formation. And in the micellars are with the polymer here, and then you get you get micellar with the polymer together, and this is high surfactant concentration. So this is a better slug compared to polymer alone or micellar alone. So this is a flow cell displacement process for that ends. So when we are using the linear polymer, this is a polyacrylamide, which is a linear polymer. This is a branch chain, and this one is brine. This is a flow cell. You can see This is all here. The black one is all when you're putting brine here. You can see the displacement is not much here. But in case of a middle one, the linear one, you can see a little bit more displacement of the oil. And in case of the branch change, which is the polyethylene oxide polymer. So these experiments were conducted in the University of Edinburgh. When I went there, my professor out there has conducted this experiment, and he has seen that there are different ways of displacement by polymers. So this is the water cut and oil recovery for different chemical EOR. So this is a water flood, and this is SP, ASP, and this is polymer ASP and ASP. So this is the recovery, oil recovery, and the water cuts. So water cuts. So this is the oil recovery for different the different ASP, SPP, and water flooding. What is the percentage of oil recovery and water recovery for different types of floods? So this the green one. Green one is oil rate. Oil rate barrels per day. The orange one barrels per day. The orange one you can see up to this one is up to 2014, and the black one, this one is the liquid flow rate, and the yellow one is the recovery by foam. Foam was formed. This one is foam assisted carbon dioxide flood. This is a foam assisted foam and carbon dioxide. So this much is the recovery in case of foam assisted carbon dioxide flood. So this is this particular simulation results of the co-flood experiment was done in the University of Louisiana at Lafayette when we were having the project there. So this is a diversion ratio. When we are using the foam flooding, we need to find out the diversion ratio, which is the volume of foam and divided by the total volume, total flow volume. So when a volume of foam is injected inside the reservoir, it will also penetrate into the narrow channels of the reservoir. So that is the diversion ratio. The foam is not taking a normal route; it is going and penetrating inside the narrow channel. That's all. That's why it is known as the diversion. So foam is diverting from its normal trend. So this is for the high permeability reservoir, and this one is a low permeability reservoir, and you can see the difference, the recovery rate, the oil recovery rate, the diversion ratio. You can find out the diversion. This one is foam. When you're injecting foam, this from 2 to 3 is the foam injection, and this one is water flood, and subsequently, and this is also a water flood. This area is water flood, and this foam is being injected. So this is a carbon dioxide. Carbon dioxide flood is a costly affair because on the surface you can see all these equipments, water injection. Carbon dioxide flood for the MOC should be of superior quality. Otherwise, it will lead to corrosion. So that is the oil bank, the miscible bank. It's a miscible carbon dioxide flood. So it's forming a miscible bank here. Then water followed by water, carbon dioxide alone, and then the dry water. So in between you need to give water because the carbon dioxide will vaporize. Otherwise the carbon dioxide will create lots of reaction with the crude oil, and the crude oil, the API gravity will change at the production well. So this is why, and you need to control the temperatures also. And so this is the oil expands and moves towards the producing well, or carbon dioxide and oil mix here. And this is the injected carbon dioxide and counter trapped oil. So how the injected carbon dioxide is encountering the trapped oil, and this is the carbon dioxide and oil mixed together, and this is the oil is the reduction is a miscible flood, so IFT is obviously 0, and the whole thing is becoming miscible, and it's becoming it's the oil bank is being formed here. So this is a screening criteria for carbon dioxide. For it should be more than 22 API gravity, and the viscosity is less than 10, and the high percentage of intermediate should be there, from C6 to C12 should be there. And normally in the crude oil of Upper Assam Basin, we have crude oil from C4 to C80, and now because we are sucking from the bottom of the barrel, we are getting up to more than that, C80, C90 sometimes. And so best crude was obtained at a time during the early 70s, 80s, when the crude oil was C4 to C40. So this one is oil saturation greater than 20, and of type of formation, sandstone and carbonate, and average permeability in millidarcy is sufficient. Injection rate can be maintained. So the depth of the reservoir should not be enough to allow injection pressure greater than the minimum miscibility pressure, which increases the temperature for heavier oils. So recommended depths. So these are the recommended depths of the reservoir for carbon dioxide miscible flood. And for carbon dioxide immiscible flood, this is it can go to greater depths. So our reservoirs can go for carbon dioxide immiscible flood, because we are having deeper reservoirs here. So this is a carbon dioxide flood. Additional oil recovery, oil bank, so miscible zone, water, carbon dioxide, and dry water. So this is what I have shown in a previous slide as well. So performance of carbon dioxide EOR. So you can see here the performance of injected oil expanse that I have shown in this slide. Okay, so this is the gas injection, and what is the oil rate increase in oil recovery. So this is a this is a heat forward combustion for forward heat injection. This one is a steam generator and injected well, and steam is being injected inside the reservoir. You have oil and the gas bank is formed, an oil bank, and hot water. The steam initially remains hot water, then it becomes steam. First it remains as steam, then it becomes hot water, and initially it goes through the production well. So this is a hot water, and this is an in situ combustion, and this is a high heat created in the injection well of the formation. And this is a reverse combustion, as I have told you, that inside just below the production well you have the heater here, and for the forward combustion you have the heater just below the injector well. From the injector well, we introduced injector well bottom has got a heater, and we introduced the air to it, so that combustion takes place. And then it becomes a combustion zone here. Then the coke zone, formation of coke zone. Coke zone is required to sustain the heat inside the reservoir. And this is the mobile oil, and it's a frontal advance. So by means of frontal advance story, water is being, the crude oil is being driven out from the production well. So here, similar is the case here. It is the heater here just below the production well. So the combustion, the hot waves are flowing towards the injector well. You have the air here passing through the injector well. From the injector well, we normally drive the air like just like in the forward combustion. And then the combustion front takes place here. There is a combustion because air mixed with the crude oil, and there is a combustion front here. Obviously, in case of when you're using heat as a fluid, then the API gravity and the crude composition also changes in the reservoir. The injector well will have different crude for composition than that in the production well. So effects of so this is a microbial biosurfactant biopolymer. This was a project we were having with the ONGC. I was a co-PI with Dhrubajyoti University. And then this one, actually incubation and leads to biosurfactant. It improves the microscopic displacement efficiency. And the polymer also, biopolymers also formed. It was the pseudomonas aeruginosa. The biosurfactant and biopolymers were formed, and then both efficiencies were enhanced in the reservoir. But this project is still in the early stage of development because the PI, Dr. Taposh Mehdi, expired, and the project is not being carried forward at Dhrubajyoti University. So effects of viscosity reduction, these are the studies there, effect of viscosity reduction on addition of microbes. You can see here after this one is the original oil without treatment. When it was not treated with the microbials, then it was kept fixed here because the API gravity of this oil was about 11, very heavy. And then when we treated with microbes, then it started flowing. But after some after treatment, after continuous treatment, we saw here it was flowing better. So it needs so it improves the mobility ratio of the, maybe it will improve the mobility ratio inside the reservoir. That portion is not being studied here in this particular project. This is a foam-assisted carbon dioxide flood for the depleted reservoirs of Upper Assam Basin. This is a portion of the study that we have conducted with when we are having the project between 15 and 19 with the University of Louisiana at Lafayette with Professor Fatih Bukade. That you can see the cumulative gas mass carbon dioxide, and this side is the time frame up to 2090 they have simulated, and of course with data that we generated together. And this is how the results, carbon dioxide can be stored inside the reservoir, and then carbon dioxide retained, how much carbon dioxide is retained, and the production profile of the reservoir, So from 90, they were doing the production profile was remaining steady. When we were giving the data, we have also simulated similar type of results, and we have found after certain period of time, the production profile inside the reservoir remains steady. But these type of experiments can enter at the reservoir condition can only be done not in India, outside, because I've already mentioned, because they give a candidate reservoir to the universities where they are having the petroleum department. So this is a project, this is a finding of the project of the novel EOR technique for the depleted oil reservoirs of Upper Assam Basin, and with simultaneous carbon dioxide capture and sequestration. So this is the UKRI joint research project with Professor Jiang King Fan of the University of Edinburgh. So these are the different data that we have simulated together in the software, annual carbon dioxide injection. So they have simulated up to 2049, and this one you can see cumulative stored carbon dioxide. So this is a cumulative stored carbon dioxide, the red ones. And then, so the black one, you can see cumulative stored carbon dioxide, CCS, carbon dioxide capture and sequestration only. And this one is carbon dioxide capture. This one is carbon dioxide capture and sequestration together with enhanced oil recovery. So this one, this portion of the carbon dioxide stood for enhanced oil recovery as well. And then this black one, I have told you this is only carbon dioxide CCS, carbon dioxide capture and sequestration. And this one is the cumulative carbon dioxide and CCS. So these are the different simulation results of the experiment. They have targeted up to 2049. What will be the scenario then? If you put the experimental data as of now, what will be the scenario at that time? So this is steam-assisted gravity drainage. So this was done by the students of in the lab. So different steam-assisted. So this one for temperatures, as the temperature increases, so steam-assisted gravity drainage simulation, numerical simulator, impact of reservoir permeability, the change in reservoir permeability. You can see the change in reservoir permeability is much higher here as you keep on moving. High permeable, kV to 3.6 Darcy and kH, and this is the horizontal permeability and this is the vertical permeability. So for different permeability, for 0.7 years, 1.7 years, if you do the simulation for this different period of time. So this is the nano UR. For nano UR, during 0 minute, what will happen, and 30 minutes simulation effect. So this scale will give you the recovery for 0 minute. For 0 minute, this whole is crude oil. For water flood, when we are doing the water flood, 30 minutes effect. This is the 30-minute effect of water flood. We can see here the change in the crude oil type. And for during water flood for 60 minutes, similar is the case for 208 minutes. And when we are doing the PHPA and say silica nanoparticles. The CMG software, this is done in the CMG stars. And after change water, what will happen? You can see it's going towards the left side. Almost the shell is being emptied. It's empty. The crude oil, the whole of the crude oil is being driven out. So this is the nano UR. Nano UR, this is chase water, chemical recovery, and the secondary recovery. So these are the different PHPA and silica. When we are driving silica, this is the blue one, the silica nanoparticles, 0.025% silica nanoparticles. The highest is the recovery. Although very less you can see here, but this much if you apply into the field, it will be much more. So this is the last one is the surfactant only. And then the polymer, it is the PHPA with the surfactant. So this is your modeling in CMG. So this is a normal modeling by the students of MTech, where you are modeling by CMG, where I will produce, given them the data, and they have done the modeling the CMG stars. And of course, in petrol also some do, but they get the good results in petrol as well. So this is a petrol RE model. One of my research students has done this model. So these are the steam lines, how it is going towards the injector well, from the injector to the producer well, the steam lines. Calculate the distance of the steam line, and we can find out the velocity profile of the steam lines. So say MUR modeling. So this is the water flooding. And when you are using MEOR, this much improvement in the recovery. So this is MEOR modeling. The flood is the recovery. This is the injector well, and this is the producer well. So the conclusion. So I conclude here, right selections of EOR process should be done for particular reservoirs, and whether chemical EOR is targeted or not. If you're targeting chemical EOR, whether it will be economical or not, that should be the right way of thinking. And secondly, I'm talking mainly of the Upper Assam basin because they are targeting more of chemical EOR. And secondly, the geophysics, the geologists, reservoir engineers should sit together in the lab and work so that they get a good enhanced oil recovery model, so that they can give it to the oil industry, which they can also implement in the field and advance. So challenges, sustained right solutions can be arrived. So for this, we need to write some projects and collaborate with the Western countries, so that we learn more from them. And in-house, they also can come here, and then we sit together and decide what to do. Things will move in the right direction. So India, I have seen in India, lots of work has to be done in enhanced oil recovery area, but in the West, they are already matured in that field. So this is a department. Thank you very much. And I have some pictures. This is a book. These are the books that were published from the department. And then these are the different papers. That is the carbon dioxide form stability. This is a paper with one of my colleagues. He has been working in this. Is Ranjan Fukan, who has done his PhD from IIT Guwahati, and his supervisor there was Professor Pankaj Tiwari. And then this is a paper, identification of the best fit crude oil of Upper Assam Basin, by one of my colleagues, this Bandita Robidas. So these are different papers from our thing. And this is a paper with one characterization and identification of the most appropriate non-ionic. I've told you that we have been working in non-ionic surfactants. So this is a paper by one of my PhD students, and this is Sidpi Sharma. And this, so this is a review one with the microorganisms. We have developed the Pseudomonas aeruginosa, and this is also being patented. So this is yesterday we had an international conference where your sir today, Dhrubajyoti, also has presented as a resource person. He has presented his thoughts there as a resource person. So these are my students with my colleagues. So these are the different labs that we are having in the department. So you all are welcome to our university when things are normal, and then you can walk with us in the lab. And so we have so many labs in the department. It's a full EOR lab, and then the core preparation lab is working very actively. And research facilities on all the students. These are some of the students, AMTech students as well. And then this is a petroleum park donated by the 17 lakhs park donated by ONGC Najira. So these are the students going to the field visit. They're going to the Rio well site, field visit out to our third semester and fourth semester students. So this is an online training program going on in the department by one of my colleagues, Dr. Barak Hamid. Thank you very much once again.
Thank you, Madam Professor Subrata Borgohain, HOD of the Department of Petroleum Technology, Dhrubajyoti University, for your excellent presentation. It was a very informative, enlightening, detailed, and engaging session. We appreciate you making your time, in spite of your busy schedule, to speak to this FDP and for enlightening us all with your nice presentation. We are very thankful to you for sharing your outstanding laboratory results with us and for talking about different UR processes, chemical UR processes. We have been highly benefited listening to your excellent presentation. Before we end this session, I would like to request Madam to be with us for a couple of moments so that we can take a group photo session with our resource person along with the participants. Participants are requested to turn on their videos for the photo session. So I would like to thank all the attendees also for being in this session and making it a successful one. We'll meet again tomorrow at 10 a.m. for the technical session. Thank you and have a nice day ahead.